Okay, the next topic is center of gravity and moment of inertia. And what do I mean by center of gravity? Well, it's a balance point, basically. So for instance, suppose we had a randomly shaped area like this. The point at which that balances gives me the center of gravity. For instance, suppose I took a random shape and I cut it out of a piece of cardboard like this, and it's got a certain thickness. And I took that piece of cardboard and I balanced it on my fingertip. Then the point of my fingertip would give me the centroid of that area. That's, in a sense, a simple way to find the centroid of an area from a experimental perspective. Now, just to let you know, it may be, if you try this, it may be difficult to find that balance point using only your fingertip. And a different way to do it would be an alternative way to find that balance point is to take a pencil and hold the pencil out horizontally and balance the cardboard on the pencil, and then you determine, essentially a balancing line. So you have a line on your cardboard, then turn the pencil 90 degrees and get a second balance line. And what would happen is that the intersection of those two lines would be the balance point, which is the centroid. So if you try this out, you can do, that's one way to find it from a more practical perspective. And the balancing line, essentially what's happening is that the moment due to the weight of that piece of cardboard on one side of the balance of the line of the pencil is equal to the moment caused by the weight on the other side of the pencil. And if we start to look at it, so we're going to start to look at this from a perspective of taking little areas here. And for instance, suppose I have a little square here, and the coordinates of that square are xi, yi, and we're going to take moments about the x and y axes, for instance. What would that look like? So, in other words, I'm going to take moments, for instance, if I take moments about the y-axis, it's the same thing, and that moment is what? Is perpendicular distance times force. The force is the weight of this one point. The perpendicular distance is that distance right there, which is my xi. So if I take xi times wi, that is going to give me the moment caused by the weight about this y-axis. Similarly, if I want to take moments about the x-axis for that little weight, it's going to be that distance, which is yi. So yi times wi gives me the moment about the x-axis. And I can take the sum of these to do, every little point on this area, some of these, and that would give me the total moment about that axis. Now, we can also use wi. How can I get wi? Well, if I have a certain thickness, the thickness is constant, and the density, the weight density is constant, then I know that the area here times the thickness, A times T, gives me the volume of that. And then A times T times the weight density gives me the weight. So I can replace the Wi with an AIT times gamma. And I'll just note that T and gamma are constant in this situation. So what we're taking the sum of the xi ai and the sum of the yi ai to get the moments about the y-axis or the x-axis. Now, why do I want to do that? Because my goal is to remember, replace the I want to find the centroid, because once I find the centroid, then I can put, to do an analysis, I can put all of the weight at that one point. Just like we did when if you remember, we had our triangle here on our beam, and I found the centroid of that triangle using the 1/3, 2/3 rule. Then I put the total load to find my reactions at that point. So that's one of the uses of the centroid, is to be able to put the entire weight or something at that one centroidal point. So now, suppose, for instance, that our origin in our x and y is at the center of gravity. Now, let's just say that happens. So in other words, I found, in a sense, my origin for my axes is at the balance point. In other words, I put my pencil in this direction, I put my pencil in that direction, and I got the balance point, and then I put my coordinate system there, for instance. When that happens, then I know what? Like I said, when we have that balance point, the moment caused by the weight on the left part of this is the y-axis, right? On the left part of the y-axis, in other words, the moment due to the weight on this part of the y-axis is equal to the moment caused by the weight on that part of the y-axis. Hard for me to show because it's not in 3 dimensions. But now, and so therefore if I find this, where this occurs, then I know I found the centroid. Now, so we have our weight is AT times gamma, like we said, and the total area is what? The sum of the AIs. Now, that means that if I establish this, we're going to call the distance x bar, or the coordinates x bar, y bar are equal to the coordinates of the centroid. So our goal is to find this x bar, y bar when our coordinate system is not located at the center, at the centroid rather than with the I'm not going to be able to do this most of the time. So I'm just going to have my, for instance, my x, y, and z, my x and y coordinate system here with my weight out here, and I need to find the location of the centroid of this, and so it's going to be located at x bar, y bar. So my goal is to find that x bar, y bar, and to find that, then we know that if I take the total weight here, so In other words, the total weight being put right there at that point, which is at the centroid, I'm going to get the moments equivalent. In other words, if I go x bar times w, that is going to be equal to the moment that we took over here, which is my sum of the xi wi. And similarly, if I take y bar times w, then that's got to be equal to the sum of my yi wi. So what we have then is that we've determined that, for instance, our x bar times w is equal to what? The x bar times the volume, which is at times gamma for the entire thing. And I know that that's got to be, as we said, got to be equal to the sum of the xi ai t gamma. And we see, of course, since t gamma are constant, we can cancel those out. And so I can solve for x bar in this equation, and I can do it similarly for y bar times w. It's going to be the sum of the y bar ai. So solving for x bar and y bar, I get that x bar is sum of the xi ai over sum of the ai. And so, yeah, I skipped a step. The area is equal to the sum of the ai, right? And similarly, y bar is going to be the sum of the y bar I ai over the sum of the ai. In integral form, so I'm not going to do this, but in integral form, I would just substitute the integral sign for the summation. So x bar is equal to the integral of x bar dA divided by dA, and y bar is equal to the integral of y bar dA over dA, where in this formula x bar is the centroid of the dA when we do this in an integral form, and y bar is the centroid of the dA that we use. Now, we're going to start just by using the summation rather than the integral. So let's focus on these. And so again, when we break up what we're going to do is we're going to break up a large body into pieces, but not so tiny, into pieces, but we're going to break it up into rectangles and triangles. And so when we do that, we're not going to use infinitesimally small divisions. And when we do that, we need to get the centroid of each individual piece. And so then the equations, so instead of this just being xi, it's got to be x bar I. And instead of yi, it's got to be y bar I. So, okay, so, you should memorize this, but you're going to be using it in later classes. So, as an example, find the centroid of this whole thing. It's made up of, well, you can see the dimensions. It's 3 inches, 4 inches, 3 inches. And I've got a triangle up here, and I've got a rectangle down here. And so the first thing we have to do is set up a coordinate system. And we're going to use the lower left corner for the origin. This is sort of standard practice. But you don't have to, but this is what I want us to do. And we're going to break it up into parts that I just mentioned. So I'm going to put my coordinate system here at the lower left corner. I'm going to break it up into area 1 and area 2. And you can see that, you can figure this out. Area 2 is 4.5 square inches because, 1/2 the base times the height, 1/2 3 times 3. And the rectangle is 3 times 4, so it's 12 square inches. And then I'm going to note where the centroid of each piece is. Well, I know what? I know the centroid of a rectangle is at the center of the rectangle. And the center of the rectangle, in this case, is what? Is 1.52, because these are 3, 4. And, and I've set my origin here in the lower left corner. I know where the centroid of the triangle is. It's, I use the 1/3, 2/3 rule. So it's going to be 1/3 in this, 1/3 of that leg, 1/3 of the leg in that direction. So that's going to be 1/3 of 3, which is 1. And then I'm going to be 1/3 in this direction. And again, it's 1/3 of 3, so that's going to be 1 inch. But my coordinate system is not my coordinate system is not here. My coordinate system has the origin down here. So when it's down here, then the full distance to this point is the 4 plus the 1. So in the y direction, it's 5. In the x direction, it's just 1. So the coordinates of that point are 1, 5. So I get the coordinates of the centroid of each of my areas, and I can write them down. So I have 1.52 for area 1. I have 1.5 for area 2. And then I note what the areas are. So then I can plug into my equation, which is what? It's the sum of the x bar I AI over the sum of the AI. Sum of the y bar I AI over the sum of the AI. So how do I translate that? Well, that's x bar 1 A1 plus x bar 2 A2 for the numerator. This numerator is y bar 1 A1 plus y bar 2 A2. And the denominator is going to be A1 plus A2, sum of the A's. A1 plus A2, sum of the A's. And then I just plug everything in. So I look here, and it's just a plug-in. And so I just take my x bar 1, A1. X bar 2, A2. A1, A2. It's just a plug-in. It's very simple. And I work it out. It's 1.36 inches. I do the same thing. You can do it for the y bars. Notice the denominators are the same. It's A1 plus A2. So once you've done it once, it's not very difficult. And you get 2.8 inches for the bottom one. So that means that my x bar is 1.36 inches. My y bar is 2.8 inches. And that means that here's my area, and I find the overall centroid and the balance point. I find it located right there at 1.36, 2.8. And I found the centroid. Okay, so here's a homework problem for you. It's composed of 2 triangles. All the dimensions are given, but there's a triangle there and there's a triangle there. And I want you to lay it out there such that the coordinate system looks like that. I have my origin there. And so I want you to solve this. Basically, you need to find where the locations of the centroids of each of those are. That's your main, but they're both triangles. So you use the 1/3, 2/3 rule to get the locations of each centroid for those and then you get the right coordinates. So in other words, once I locate that one there, you need to get that distance and this distance. And for the other one, you know, the centroid is over in here. You need to get that distance and that distance. So do that, get the areas, and plug it in to get use the. All right, so pause the video here and solve this one. Okay, so again, using the 1/3, 2/3 rule. So if I'm looking at the upper triangle, I know that that it's in this direction. It's 1/3 times the leg length. The leg length is 1.8. And in this direction, it's 2/3. So it's 2/3 times the leg length, which is 2/3 times the length of the leg, which is 3. And for this one, it's going to be 2/3 times the leg length of 2.7. And it's 2/3 times the leg length of 7.2. So I have these distances, and notice that for area 1, I have the x bar is that, the y bar is that. For area 2, I have this is the x bar, so that's right. Or sorry, yeah, 2/3 of 3, which is 2. And but for the y bar, I have to add in, I know this distance, but I have to add in the extra for so in other words, I want the coordinates of that point, so I have to add those two distances together. I need this full distance, which is going to be the 2.7 plus the 0.6, so it's going to be 3.3. And then I can get the area, 1/2 the base times the height. You can all do that. And then I just fill it in. It's going to be x bar 1, A1 plus x bar 2, A2. And the other one will be y bar 1, A1 and y bar 2, A2. And both of them have A1 plus A2. A1 plus A2 in the denominator. So then I just work it out. Work out the math, and that's what I get. So I now have the location, 4.19, 2.13, and I can put it onto my area right here. So this distance is 4.19, and this distance is 2.13. So I now have the centroid of this whole area there. And like I say, if you cut that out, that would be the balance point on a piece of cardboard. All right, here's another one. Now I have 3 areas, or it looks like a teardrop, but I have a semicircle here. I have a triangle here and a triangle here. Now the semicircle, I'm going to give it to you where the centroid is located. So it's a semicircle, so this is dead center. I'm dead center in this direction. But where am I in that direction? Well, I'm 4r over 3 pi from the top. So in this particular case, this is a semicircle with a radius of 1.5 meters. So that distance is 4 times 1.5 over 3 pi. So that's going to locate the centroid for you for that piece. And of course, you know the area of a circle is pi r squared. And so it's a semicircle, so it's 1/2 pi r squared for a semicircle. But okay, so what you need to do is fill out this table for these 3 areas and find the location of the centroid. Okay, so pause the video here and do this one. All right, so I fill out the table. Area 1 is the semicircle. It's, 1.5. This whole distance is 3. So the x bar to the centroid there is 1.5. We've set up our coordinate system such that the origin is down here, and then how do I figure out my? I have 4 times 1.5 over 3 pi, which I take, and I have 1.5 minus 4r over 3 pi. And that, I guess I haven't gone through the math here, but that works out to be 0.863. So that is here. And of course, the area is 1/2 pi r squared. For area 2 here, again, I use the 1/3, 2/3 rule. So I've got 2/3 of 2 in that direction, which is 4/3, 1.33. And then in this direction, I'm 1/3 of 4, but I have to add that to the 1.5, and that gives me 2.83. And it's a triangle, so it's 1/2 the base times the height. For this one here, for area 3, again, I'm 1/3 of 4 plus the 1.5. So the y bar is the